What we can do is relate our first derivative, which is finding the instantaneous rate of change for our graph, and relate it to where our original function is increasing and decreasing. What it's going to come down to is the sign of our first derivative. When our first derivative is positive, then that's where our function is increasing. So our original function, f of x. So let me specify that. So our first part of the rule, if f prime of x is more than 0, so if our first derivative is positive for all x in an interval, then f of x, our original function, is increasing on that interval. So where we have a positive derivative, our function is increasing. If f prime of x is less than 0, so if it's negative for all x in an interval, then our original function f of x is decreasing on that interval. So where our derivative is negative, our original function was decreasing on that interval. If f prime of x is equal to 0 for all x in an interval, then x is constant on that interval. So that would be where we have a horizontal line because there's no rate of change there. So we would have a flat function there. If f prime of x equals 0 at a single point, we call this a critical value. And that's going to be something important that we need to find in our work. So let's go over to Desmos and take a look at x cubed minus 6x squared. So this is a cubic function, so it increases up to the point 0, 0, and then it decreases down to 4, negative 32, and then it increases off to positive infinity. So we're calling this our original function here. So some things I could note about this. So reading the graph, like I said, so we can see that we're increasing from negative infinity to 0. We're also increasing from 4 to positive infinity. And then we have this interval of decreasing from 0 to 4. So in all of these spots where our function is increasing, we're going to be seeing positive derivatives there. And anywhere where our function's decreasing, we're going to see negative derivatives. Now there's no part of this function that's flat, or there's no part of this that looks like a constant function or a horizontal line. So with that, we're not seeing any spots where, or rather an interval where f prime of x equals 0. However, we have coordinates where f prime of x equals 0. And those are the spots where we're changing from increasing to decreasing or decreasing to increasing. So this coordinate 0, 0, this local maximum, if we take the derivative at that point, we're going to have a derivative of 0, because right at that point, our instantaneous rate of change, or that slope of the tangent line, is flat. We'd have a horizontal line just at that spot. Same thing at that local minimum at 4, negative 32, that's going to be a spot where our derivative equals 0, and that's where we'd be changing from decreasing to increasing. So these critical points are important to kind of separating up these intervals of increasing versus decreasing. Let's take a look at the graph of the derivative of this. So if our original function is x cubed minus 6x squared, if we apply our power rules, we'll have 3x squared minus 12x for the derivative. So when I graph this, what you notice is it's a parabola. So it's a parabola that's decreasing. It hits a minimum at 2, negative 12, and then increases up. But what we can see is, so our parabola has positive output values all the way up until x equals 0, which makes sense because on our original function, our function was increasing until we reached x equals 0. So notice that our function has the coordinate 0, 0 for the derivative, and that's because when x equals 0, the derivative is 0. So that's where we hit that little local maximum in our original function. And then the parabola dips under the x-axis, so we're seeing negative output values all the way between 0 and 4, which makes sense in terms of our original function because that's where our original function was decreasing. From x equals 0 to x equals 4, our original function was decreasing, so that's where we're getting these negative output values for our function. And then from there, we have the coordinate 4, 0 on this derivative function, which also makes sense because that was our turning point. So at x equals 4, our derivative was 0 because of that local minimum where we were switching from decreasing to increasing. And then our original function was increasing from x equals 4 to positive infinity. And that's where on this parabola, we're seeing positive output values starting at x equals 4 and going off to positive infinity. So if we look at our derivative function, all of the spots where x is positive, that's where our original function was increasing. All of the spots where our derivative function is negative, that's where the original function was decreasing. And then crossing the x-axis with our derivative function, those were those critical values, so those points that were turning points on our original function. So with this, we can relate these two pieces. What we're going to do is focus on the critical values because that's going to separate up these intervals of increasing, decreasing. And then what we could do is just find the derivative in certain intervals to figure out whether or not it's positive or negative, which will tell us increasing or decreasing, which I know that's a lot of wordage there and maybe your mind is spinning, but once we get some examples, you'll see how we're applying this, and we'll apply this to that cubic example that we just went through too. So the first derivative test allows us to find intervals where our function is increasing and decreasing without graphing our function, and we can do this with using the derivative. So our first step is to locate the critical values. So what we're going to do is look for where is our derivative equal to 0 or undefined. So we're going to find all of those spots. What we're going to do is select a test value from each of those intervals. So it's going to be a value for x that's landing in those intervals that we can evaluate the derivative. So that's our next step, is to determine the sign of f prime of x in each of those intervals. If it's positive, it's increasing. If it's negative, it's decreasing. If it's equal to 0 in that interval, then we're seeing a constant function. So let's go through some examples of how we apply this. So find the intervals where the function x cubed minus 6x squared that we were just looking at the graph of is increasing, decreasing. So let's look at finding those critical values algebraically. So f prime of x, taking the derivative. So the derivative of x cubed is 3x squared. Derivative of negative 6x squared is negative 12x, using the rules that we just learned in those previous videos. All right, so I want to see where is this equal to 0. So 0 equals 3x squared minus 12x. And now we're going to do some factoring. So 0 equals, I can factor out a 3x, and that will leave me with x minus 4. And now we can use the product of zeros rule. So 3x equals 0, x minus 4 equals 0. So I'm getting x equals 0 and x equals 4, just like we saw on our graph. So those were our turning points, x equals 0, x equals 4, and that's where our derivative is equal to 0. So now what we're going to do is this determines the test intervals. So what I'm going to do is set up my intervals. So I have these cutoff values at 0 and 4. So what I'm going to do is have these intervals so I can go from 0 is the smallest of the two. So we can go from negative infinity to 0. And then my next interval will be between 0 and 4. And then my next interval will go off from 4 to infinity. So when we set up these intervals, we're going to incorporate negative infinity and positive infinity. And then we use these values, those critical values that we found, as kind of cutoffs for the interval. And just make sure you're going in order from smallest to largest. All right, so now what I'm going to do is look for test values. And what this does is we're going to we're going to select a value for x that's landing in these intervals. So like I need a value that's between negative infinity and 0. And there are infinite possibilities here. I try to go with the simplest of numbers. So I'm going to use a -1 there. And then 0 to 4, how about I use a +1 is in that interval. And then 4 to infinity, 5 is that interval. So where we have all of those test values, what I want to do is evaluate f prime at those test values. So I'm going to use that f prime of x, so we already found that 3x squared minus 12x, and what I'm going to do is plug in these different values. So 3x squared minus 12x, if I plug in -1, so 3 times -1 squared minus 12 times -1, so that's going to be 3 times 1 plus 12 is 15, so that is positive. That's really all I'm interested in, if it's positive or negative. If I plug in +1, so 3 times 1 squared minus 12 times +1, so 3 minus 12, and that's a -9, and that's negative. That's what I'm interested in. And then if I plug in +5, so 3 times 5 squared minus 12 times 5. So let's see, 3 times 25 is 75. Minus 12 times 5, which is 60. So this is going to be a positive 15, so positive. So what I can see here is where my function is increasing or decreasing. So that test value of -1, which is in that interval -infinity to 0, because that was positive, it's increasing on that interval. 0 to 4, where we plugged in +1, we got a negative value out, so we're decreasing on that interval. And 4 to infinity, plugging in +5, we got a positive number out, and that means we are increasing on that interval, which is what we saw in the graph. We saw increasing, then decreasing, then increasing. So our final answer, intervals for increasing, our function is increasing from -infinity to 0 and 4 to infinity. And then our function is decreasing between 0 and 4. But all of this was done without using the graph. We kind of talked about the graph first so that we knew what to expect, but this doesn't require any graphing. This is just using our first derivative, and positives and negatives is what it comes down to. All right, let's find the intervals where the function 1 over x to the 2/3 is increasing and decreasing. So our original function, I'm just going to rewrite it as x to the -2/3, which means our first derivative is, let's see, the -2/3 will come out front, and then we'll have x, and then we need to bump that down by 1, so -2/3 minus 1 should be a -5/3. Okay, so we want to see where is this equal to 0. So 0 equals -2/3, and actually I am going to rearrange this. So I'm going to do -2 over 3, and then x to the -5/3, I'm going to bring that down to the denominator, so that it's x to the +5/3. All right, so I need to move things around, and what's going to happen is if I multiply both sides by this 3x to the 5/3, which is exactly what we'd want to do because we'd want to get x out of that denominator, that's going to turn into 0. Like we're going to end up with 0 equals -2. And what that tells me about my interval, so there's no solution for x here, what that tells me is that there's no critical values. Now that doesn't mean anything in terms of our function isn't increasing or decreasing, because it absolutely is. If we graph this, we can see something's happening. So what this means for our interval is that there's just no cutoffs for our interval. If there's no critical values, there's no cutoffs. So the only interval we have is the interval, which is -infinity to +infinity. That's what we're focusing on here. So in terms of a test value, we just need to choose something between -infinity and +infinity. I'm just going to use 0. That's a nice thing to plug in to numbers, to functions. And so that evaluating our derivative at 0, so we're going to have -2 over 3 times 0 to the 5/3. 0 raised to 5/3 is just 0. So sorry, in doing that, I paused because I was like, that's going to be undefined. And that is exactly what I wanted to bring up here. We also want to pay attention to where our derivative is undefined. So let's go back a little bit. Our function, -2/3 times x to the 5/3, we want to be careful of having our derivative equal to 0. So while there are no critical values for where our derivative is equal to 0, we do have a spot where we're undefined in that x cannot equal 0. So we are limited there. That's going to divide up our interval. So I'm going to backtrack. I'm going to leave that in there because that was a very important point. But x cannot equal 0, so let's use that to separate up our function, our intervals. So I'm going to separate up the intervals, -infinity to 0, and then 0 to +infinity. All right, test values, how about using -1 and +1? So f prime of x at -1, -2/3 times -1 to the 5/3. And we could use a calculator to evaluate these. These are just plugging in, so feel free to just plug into the calculator. All we're really interested in is positive versus negative. So -2/3 times -1 with an exponent of 5/3 is +2/3. And really I'm just interested in the fact that it's positive. Plugging in +1, so -2/3 to the times 1 to the 5/3. 1 to the 5/3 is a +1, so -2/3. So we're getting a negative answer out. So we do have two behaviors here, increasing and decreasing. So my explanation with the -infinity to +infinity, that would have been true if our function was defined everywhere. We have this little caveat of the fact that we can't let x equal 0. So that gave us an interval. So just going back to that explanation for locate the critical values. So the critical values are where the derivative equals 0, but also be careful of these spots where our derivative is undefined. That can separate up our interval as well. We just didn't have that with the first example because we had a quadratic, which is defined everywhere. But these cases where we have x in the denominator, we need to be careful of that. Okay, so we have an interval for increasing is occurring from -infinity to 0, and decreasing is occurring from 0 to infinity. Okay, it was kind of a long video, but let's do one more example. So x² - 1 cubed. So this is going to use a little chain rule. So we're taking the derivative. So the outside function is the exponent of 3. So we're going to bring the 3 down. We keep the inside function of x² - 1. And now we're going to have an exponent of 2. And then we're going to multiply by the derivative of x² - 1, which is 2x. So this is going to simplify to 6x times x² - 1 squared. I'm going to leave it in this nice factored form here and go from there. So we want to see where is this equal to 0. We could also at this point try to evaluate if it's undefined anywhere, but this here is a polynomial, so we're going to be all good there. We're not dividing by anything, not taking the square root of anything. Those are kind of the cases we want to be careful of. So my only critical values are going to come from where this derivative equals 0. So 6x times x² - 1 squared. So 6x can equal 0. This x² - 1 can equal 0. So 6x equals 0 is going to solve to x equals 0. So that's going to be one of our cutoffs. X² - 1 equals 0. So x² equals +1. Take the square root of both sides. So x can equal plus or minus 1. So if it helps for thinking of these intervals, you could think in terms of a number line. So we have 0, we have -1, we have +1 as our cutoff values. So our intervals, let's see, we're going to have 4 intervals. We're going to have -infinity to -1, -1 to 0, 0 to 1, 1 to infinity. All right, let's write out those intervals. So -infinity to -1, -1 to 0, 0 to 1, 1 to infinity. All right, our test values. Let's see, between -infinity and -1, let's use a -2. -1 to 0, how about a -0.5? 0 to 1, how about a +0.5? 1 to infinity, how about a +2? Okay, so I want to plug all of these into f prime of x, and what we can do is use the calculator to help us out. Again, we're only interested in positive or negative, so let's go to our scientific calculator. So, just want to make it so I can see my derivative function. So we're using 6x times x squared minus 1 squared. So let's say we're plugging in the -2 first. So I'm going to have 6 times -2, and then in parentheses, a -2 quantity squared minus 1 with that whole expression squared. And that's giving me -108. Really, we're just interested in the fact that it is negative. So I'm just going to put a negative symbol for that interval. Then we want to plug in -0.5, and what I'm going to do is just replace those values. And you can make a table of values too. I know we've talked about how to make that in Desmos, or you can use Excel to make the tables. So this is negative as well. So it's going to be decreasing there as well. Let's see, +0.5. So I'm going to go through and edit out the negative symbol. So 6 times 0.5, 0.5 squared. Now it's a positive value. And then +2. If I plug in +2, that's also going to be positive. So we have these. This is kind of an interesting one because not rarely, but it's an interesting one with having decreasing and then decreasing. Now these intervals are kept separate because at -1, the derivative is equal to 0. So it's not decreasing at x equals -1. So for our intervals, our function is increasing from 0 to 1 and then 1 to infinity. And then our function is decreasing from -infinity to -1 and -1 to 0. So let's take a look at the graph of this to see what is going on there. So it has these turning points at x equals -1, x equals +1, but the behavior stays the same. So we're decreasing, it kind of flattens, and it keeps decreasing. Then at x equals 0, we're getting a turning point from decreasing to increasing. And then at x equals 1, it flattens and continues increasing. So it's very much possible to have the same behaviors next to each other. It just means we're kind of flattening at that point rather than turning at that point. Okay, that's our first derivative test. So again, finding where our derivative is equal to 0 or undefined, set up those intervals, plug in test values, and really you kind of saw how my work got shorter and shorter for that. I wanted to show you how we were finding these values, but really what it comes down to is if it's positive or negative at those test values, because then that's going to tell us increasing or decreasing.